Welcome to The Explainer. Today we're going to talk about a really elegant graphical method that lets engineers, well, kind of predict the future, or at least the future behavior of the systems they design. It's called the Root Locus Method. So here's our roadmap for this explainer. First, we're going to figure out why we even need a map like this. Then we'll look at the mapmaker's tools, the fundamental equation behind it all. After that, we'll learn the rules for actually drawing the map, use it to solve a real-world design problem, and finally, we'll wrap up by talking about why this visual approach is still so incredibly important for engineers.
All right, so at its core, the root locus method is all about answering one single critical question that pretty much every engineer has to face.
I mean, this is a constant source of stress, right? Whether you're designing a high-speed train, a delicate surgical robot, or a massive power grid, one tiny adjustment to a single parameter could, in theory, send the whole system spiraling into instability. This method gives you a literal map of your system's stability. So instead of just trying one setting and, crossing your fingers, you get to see the entire landscape, every possible outcome laid out right in front of you. It shows you exactly where the safe zones are, and more importantly, where the dangerous cliffs are, the places where a tiny change can lead to total failure.
Every map maker needs their tools. And for the root locus, our compass, our ruler, our everything, it all comes from one fundamental equation.
And here it is. This is the characteristic equation, and it is the absolute heart of our control system. So P of S, that represents our system's dynamics, just how it naturally wants to behave. K is a gain, basically a knob we can turn up or down, and S is a complex variable that really defines the system's behavior. The roots are the specific values of S that make this equation true for any given K, and their location on a graph tells us everything we need to know. Is the system stable? How fast will it respond? Will it oscillate? It's all in there. So we plot our map on what's called the S-plane, and on this plane, poles are the starting points for our journey. They represent the natural built-in dynamics of the system when our gain, K, is turned all the way down to 0. You can think of them as the system's default settings. We always mark them with an X. So if the poles are the starting points, the zeros are the destinations. As we start turning up that gain, K, the system's roots are literally pulled away from the poles and dragged towards these zeros. Zeros can completely reshape how a system responds, and we mark their locations on the S-plane with a little O. Right, and this is the crucial point. K, the system gain, that's the knob we're turning. As we adjust K from 0 all the way up to infinity, we are literally driving the system's roots along these predetermined paths, that's the locus, from their starting poles to their ending zeros. Okay, so we've got our starting points and our destinations. But how in the world do we draw the roads between them? Well, luckily, we don't have to guess. There's a handful of really simple but powerful rules that let us sketch the entire locus. Now, there are actually 7 formal rules, but you really only need to get these 4 concepts. First, we know paths always go from poles to zeros. Second, a really simple counting rule tells us exactly which parts of the real axis are part of the locus. Third, asymptotes show us the general direction for paths that are heading off to infinity. And finally, breakaway points show us where paths might suddenly leave the real axis and jump into the complex plane. Okay, so what happens if we have more poles than zeros, more starting points than destinations? Well, those extra paths can't just stop. They have to go somewhere. So they travel out towards zeros at infinity. And asymptotes are just straight lines that show us the exact direction these paths take as our gain K gets really, really big. And what's so powerful about this is that we can calculate these asymptotes with perfect precision. The formula for the centroid, that's sigma A, it tells us the exact point on the real axis where all these asymptotes are going to intersect. It's like the hub of a wheel. And we calculate it just from the locations of the poles and zeros. Then, that formula for the angles, phi A, tells us the precise direction each path will travel, just based on the number of poles, n, and zeros, m. It's really amazing. Together, they give us a crystal clear picture of the system's endgame behavior. Now, this is where things get really interesting. When you have 2 root paths that are on the real axis, and they're moving towards each other, they eventually collide. And they have to go somewhere, so they break away from the axis and move into the complex part of the S-plane. And this is a hugely critical moment, because as soon as those roots become a complex conjugate pair, the system's behavior fundamentally changes. It goes from a smooth response to an oscillatory one. This is where you start to see things like ringing and overshoot. And we can find this critical transition point exactly using a little bit of calculus.
We just rearrange our main equation to solve for k, and then we find the spot where its rate of change with respect to s is 0. That gives us the precise location on the axis where the breakaway happens. This tells the designer the exact value of gain that will cause their system to start oscillating. All this theory is great, but let's see how this map-making process really works in the real world, especially when things get a little complicated. Like, say, designing a system where you have more than one knob to turn. So here's our challenge. We need to control a robotic welder with extremely high precision. And the system has two different knobs we can turn, two different gains, K1 and K2. Our job is to find the absolute perfect combination of these two values to meet some very strict performance goals. And here are those goals. First, it has to be really accurate with low error. Second, the damping ratio, that's zeta. It has to be high enough to make sure it doesn't overshoot its target too much. And third, the settling time has to be super fast, under 3 seconds, so the welder can get to work right away. So how do you map a system with two independent knobs, K1 and K2? Well, you use this really clever trick. You just tackle them one variable at a time. First, we pretend K2 is 0, and we draw the entire root locus just for K1. This first map lets us pick a good starting point for K1, in this case, 20. Then we lock K1 in at that value, and we draw a completely new root locus, but this time varying K2. This second map is what shows us how to fine-tune the system to meet all our final design goals. And here it is, the final design check. With our chosen gains of K1 equals 20 and K2 equals 0.218, we get a damping ratio of 0.71, just enough to stop that overshoot. The settling time is a lightning-fast 1.26 seconds, which is great. And the error is well within spec. This two-step mapping process led us straight to a design that meets every single one of our requirements. Success! So, beyond just this one example, what's the big takeaway here? Why has this graphical method stayed so important, even in an age where we have incredibly powerful computers? This quote just nails the true power of this method. It's not just a tool for finding one single correct answer. It's a tool for understanding sensitivity. When you look at the map, you can actually see how the system will react to changes. Are the paths all tightly clustered together? Your system is probably pretty robust. Do they shoot off in wild directions with just a small change in gain? Well, your system is sensitive and probably fragile. And that visual intuition, that's what separates a good designer from a great one. Ultimately, the root locus method does something pretty remarkable. It turns really complex algebra into intuitive geometry. It gives engineers a form of foresight, letting them see all the hidden trade-offs in their design. It's all about making sure that things don't just work on paper. They work robustly out in the real world. And that leads to a final thought. If you could map the stability of any system just to see its hidden flaws, what would you choose?